So, oh, look at that. All right then. Homemade foods. All right. I think we're. So I'm actually. It's really good that I'm going after Shane, because this is an application of some of the stuff you just saw. And in fact, the thing that I'm going to show you tonight is something I've been working on, and I don't know how many emails have gone back and forth between Pete, Shane, and myself on this particular project, but I'd like to think that I've taken some of the things that Shane talked about and you know, what Pete has talked about as well, and put them to some good use. So, but before I get into that, I have one quick thing. We all kind of promised that as we got our all pixels, we'd show what we did with them. And I finally got around to think we have people coming over, and we're going to be doing, you know, having a party at our house. Wouldn't it be great if I had something I could show off to everybody that's coming over? And so I finally put this thing to work. I got some 1/4-inch molding frame, and I took apart, and I bit the bullet and bought a Raspberry Pi. I'm really
Wait a minute, what do you mean bite the bullet?
Yeah, no, I know, it's really embarrassing. So I actually put this in a drawer so no one could see it. Inside the drawer, there's a little Raspberry Pi, and hooked up with the all-pixel and a nice 10 amp power supply. And then I ripped our entertainment center apart and put this stuff on the wall behind it, and then put it all back together so it kind of looks like this.
And you're still married?
And well, yes, but, and I'll so yeah.
Does anybody have a garage you
Yeah,
can
so I actually, so now it's got this really cool, I think it's really cool, you know, Larson scanner kind of thing going on, and at night when it's dark, that little frame above it's got like the light comes through, and it's really fantastic. So anyway, I'm just showing you that all pixel thing is fantastic. I'm having a lot of fun with it, and you know, maybe we could all just, you know, as we put these things to work, we can show what we're doing with it. The part about the butt is, I realized that once I put this in place, my wife has opinions on the colors and the animations and all this, and I wasn't anticipating that. So she like, why are all these different colors? And no, it should just be one. And
Well, it's nice to be married to an architect.
yeah, so anyway, so but yeah, I'm actually using the all pixel, and the thing is amazing. It's caused me to buy a Raspberry Pi. Now I'm learning Python, but it's really having some fun with it. And I'm going to I'll document how all that stuff works, you know, in case anybody wants to try to do something like that. So the thing I was going to talk about tonight is this Arduino control testing control board, and the idea is that this guy took a little while and did it. Why am I still doing it? Because I've been at this for a little while. This is like we're working on now Rev 4, and then what this thing looks like, and then give a quick demo and some lessons learned. So the reason I did it is I get tired of this after a while, right? It's a mess. One of those wires comes out, and then you have to figure out which one it was. But what I oftentimes need to do is like hook up an Arduino and have it do a particular thing, and I figure, okay, I'm going to hook up an I2C based device or an SPI based device, or I'm going to need a real-time clock so I can log values at certain times. And you know, I after a while I got tired of the breadboard thing, so I decided to build a board that would do it, and that's the one you see here in the middle. And this is actually exercising one of my trail counters. This is a GPRS-based trail counter thing that Shane, the one I gave to you. This is it in prototype stage, and that thing just kind of runs it through a test program. It just watches the thing, makes sure it's doing what it's supposed to do, and it logs it so that I don't have to hook up my computer to it, and I can just turn this thing on and walk away for days, and it will just run and come back at the end of it. I can get a log of how it performed, and how long the battery lasted, and how many times it transmitted, and all those kinds of things, which are, you know, kind of good to have. But the thing is, that board was really big, and if you try to go to Osh Park with it, it was like $50. So I ended up getting it from China, but then it took a month. And the display kind of frustrated me because I couldn't do very much. So I decided to take on a new version of it, better display, I had completely hosed the MOSFET piece of that thing up. I just got all the connections wrong, I didn't talk to Shane enough, and so I wanted to take another run at the MOSFETs. I wanted to be able to turn on and off not only the load, but also to turn off the source as well. So basically the Arduino would be able to completely turn off the test if, let's say, the thing exits a certain parameters of temperature or time or values of voltages. Because, for example, if you're doing a lithium-ion battery, you damage the battery if you drain it below a certain voltage. Or if you're running in a certain envelope for the power supply, at certain times you're working it really hard, it can heat up and you can end up damaging the power supply. So I wanted to be able to turn everything off I needed to. I wanted to be able to high voltage and high current. Like some of my things now are solar powered, and some of these solar panel cells are basically 6, 12, 18, they're multiples of 6, the popular solar panels. So I wanted to be able to do higher voltages, higher currents. I want a smaller board so I could spin and respin the thing through Washpark. I want some test points, and then I wanted to be able to turn this thing on and leave the house and not worry about this is going to catch on fire or damage something or whatever. I wanted to be able to have it, kind of monitor itself and manage the process. And then importantly, this time I didn't go alone. I reached out to Shane and Pete, and we have had a real lively discussion about what this thing should look like. So what I ended up with is something that looked like this. It basically, in the upper right, you see it's an Arduino Mini that's controlling the thing. I just use all the pins that little device has to offer. I put SPI, I2C, and analog headers, for future use. And I put a nice display, real-time clock, and a high-side current sensor because I wanted to be able to, like I said, go to higher voltages and higher currents than the Arduino can handle. And here's the cool part, it can turn on and off the power that you're testing, the power supply, using a PFET, which we didn't show as much on, but the PFET for turning on and off the source, and an NFET for turning on and off the load. And the idea was, with Shane's help, actually, I can switch them on and off enough that I can do pulse width modulation. So I can basically set a load profile that will change over time so that I can basically exercise the complete envelope of a supply. And then either the device or the supply can test is here, and then I added these test points so that, someday if I go to Pete's house and he's got this wonderful oscilloscope that's going to be working, then, we could hook up to that. Or if I got my little, what's that, I can look at the transients in the response, let's say, to a spike in current or the load that goes up. And then Shane convinced me to put an AC load with a solid state relay on there, but it's more for play, and we haven't really done much with it yet, and we'll see what it looks like in the next shred. So the board ended up, actually got it down to about a third of the size of the last one. Part of that is because I just used a much smaller OLED display that just had higher density. But I also tried as much as I could to make things physically as tight a fit as possible, and I'll show you what that looks like. But the one thing that's kind of cool about this, it's a little hard to see from this, so I'm going to switch over to Eagle, is how to do the supply where it can handle a decent current. And so, let's see if this shows up. So this is the board itself in Eagle, and to date, I've been very used to this idea of connecting things with the little nets and having the vias and all that, and I ended up routing this stuff, and I'm pretty comfortable with it. But with this one, we wanted to be able to handle higher currents. And these MOSFETs, if you look, like this is the P MOSFET. It's got the gate, which has got just one pin, and then it's got the, I'm going to get this wrong, drain? No, that's a P.
Those are
Source. And then the drain has got, but all four of these pins are connected. So that's how it gets as much current through that as it can. And what I found was when I was connecting it with the trace, I wasn't able to get enough width, enough copper into that thing that I could get a decent current through. Yeah, good question.
Dotted polygons are pores.
Yes, and so what we did was, we came up with this idea of the high current path to this thing is now all pores. And I'll show you what that looks like in a second, but the idea is that instead of just connecting this with a trace, this pore goes from here to here.
What's a pore?
So a pore is a polygon that's defined, and basically you tell Eagle that within these dotted lines define an area. See, so I'm tracing with my finger here, and it's saying everything just pour copper
Oh, I see.
inside that polygon. And what happens, and this is the cool part, and I'll just zoom in and show you. So I'm gonna show you what a pore looks like. This is the P MOSFET. So you can see the gate on the bottom left with the trace coming out. You got the source on the left, the 3 pins you see on the left, and then you get the drain on the 3 pins on the right. And now when I pour the copper,
Is the bottom pin on the right not used?
Bottom pin, 4 pins on the right.
all these pins are used.
Oh, okay.
And you see what happens when you do a pour, you get each of these pads now gets 4 connection points, whereas typically when you're just using a trace, you just get 1. And then the amount of copper around those pins is significantly greater. And because of that, you can bring a lot more current through the circuit, and what you end up with is a circuit that's actually kind of cool to look at, but you can see now the regions are all the pores, and you can follow the path. The hard thing about this is you can't do a via with a pore, right? Because that kind of defeats the purpose. So I had to lay this thing out where each of these pores, basically the current comes in, this is ground, right? Here's my VN, and basically it had to flow all the way through, basically without any kind of a break that would cause me to have to use a via to get over to the other side of something. So everything had to be kind of jumbled around. But that was something that we all worked through. This first time I ever did it, it's pretty cool, and once I got the hang of it, it actually worked out really well. So that was one thing I learned on this. It was kind of new.
It almost looks like a ground plane.
I know, yeah, exactly. I'd always used the pore for
Yeah, that's what I'm,
ground before.
yeah.
You put the big polygon around the whole board and just say ground. But in this case, so I still did that. It's just that now my ground pore, basically all this is ground pore over here. But yeah.
The other thing, you may not touch on this, but right in the middle, there's, well, it's not in the middle anymore, but
Oh, sorry.
down at the bottom,
Yeah.
isn't that one of your, where's your sense resistor?
Yeah, the sensory
right,
system
oh,
already.
there they are.
Yeah.
So
One.
those pores are creating
Here.
fantastic heat sinks. So the power dissipation through those resistors,
Yeah.
it's not just the transistors that are benefiting, but
The-
other things that are going to dissipate heat.
Yeah,
The
they're
design
heat
of the
spreaders,
system
they're not
is
just
really
conductors,
good.
they're heat spreaders also.
Yeah.
Yeah, good point. So one of the ways that I wanted to be able to sense higher voltages was by setting the analog inputs on the Arduino as close to ground as possible. So these are 0.1 ohm 1206 resistors. And the analog inputs, as well as the test points for the oscilloscope, would all be right at the high side of those resistors, so that they're going to take a fair bit of current through it, but they're low resistance. So we figured, we sized it for about I think in the end it sized it for like 10 amps, but who knows?
I think weren't they 25 mil resistors, not the 12?
I thought they're 1206, but I have to go back and see.
The double. I thought they were.
I was doing electrical.
Yeah.
So
Well, anyway,
So Pete, given this is all this copper is in essence a heat sink, do you have to really properly heat up the board if you were going to put components down? Because you're,
oh yeah, well, this would affect the soldering.
Yeah.
This would affect the soldering, yeah, it's
yeah,
definitely the
so
case.
you'd have to, and then, yeah.
You may have to adjust, the hand soldering is going to be noticeably different.
Right.
Yep.
And with reflow, you have to take that.
That's why they have the little ring with the pluses. Without that, it would be even more difficult to solve.
Right.
Okay.
Yep. Yeah, exactly. Yeah, that's why, for example, on this pore here, if I zoom in, That's why those pads aren't just completely
Oh.
connected,
Mhm.
because then
Because
it would
otherwise
be very
It would be
difficult.
sucking the
Yeah.
heat out as fast
Yeah,
as.
as fast as you're putting it in.
Right, exactly. So it's a bit of a balance between wanting to get as much copper in so you can get as much current through, and then, but then limiting it so you can still reflow. I hand soldered this one, but it would be an interesting, maybe on the next rev, it would be kind of cool to try a reflow with it and see how that works. I suspect it would be, might be a little bit of a challenge, but who
No,
knows?
no, no.
So this board kind of looks opposite of what you typically see for traces, because normally I look at the blue and I go, oh, trace. This is now insulation.
Yeah, so the blue is the bottom, and the red is the top. It's a two-sided
So
board.
blue's bottom copper.
So the bottom copper is blue,
You can turn
and,
the blue layer, bottom layer off.
yeah, so let me show you. So if I come in here and I turn off the bottom layer, that's what, this is just the top copper.
So all of the red is copper.
Yep,
All the red is copper.
All blue is copper too, but on the other side of the
That's
board.
correct.
there's no blue anymore.
Yeah, so if
Now the black is insulation.
Right.
So you can turn the red off and turn the
That would
blue
be
on.
the board itself,
Yeah,
which is an
So
insulator.
you have as much copper, that board's 90% copper.
Yeah, exactly.
Yep.
Yeah, and that's what was kind of unique about this board, because typically, I probably still would have done a pour, but it would have just all been ground. But here, you've got that whole piece starting from here and taking you all the way through to there is is copper, to get as much current through as possible.
So it gives you as high conductive path as you can possibly get, so you haven't wasted any of the potential performance. You've got.
Did you calculate your maximum current that you could potentially?
Well, yeah, so that's a good question. There's trace width calculators that you can go in and use, but they are based on the idea of having a trace. And that when you have a pour, I don't have an easy way of calculating it. So what we ended up doing was putting in these resettable fuses, these PTC, and I'm not sure what that stands for.
Positive temperature coefficient.
There you go. So, so there's one here that sets a limit on how much current will be allowed through the current path, and then there's one over here that kind of protects the amount of current that the Arduino is applying to the display, the real-time clock, and the sense. But I was going to actually, one of the things I want to do, and this is something that now Pete's got a new piece of kit that we can play with, is, we could take this piece and replace it with a wire, and then start looking at with an IR camera and see, how hot things get.
Because I have a FLIR infrared, I
Yeah.
would love
Yeah,
to.
that's what we're talking about.
Yeah,
Exactly.
I have and I mean, it's really sensitive.
And
I would love to pump some power and look at the cross-section.
we'll be doing, yeah, so maybe the next time we'll have some cool.
Yeah,
Yeah.
and the other thing that we can do, I got some equipment, and we can put arbitrary pulses through this thing. We can, programmable power supplies and
Programmable loads.
programmable loads,
Yeah.
and just have a party with it, with the oscilloscope, and see what it really does. And I
Right.
predict that it's gonna have no trouble switching 6 amps.
Yeah, that's the
Piece
whole.
of cake.
But the one thing, I do know, this is version 3, I do know there will be a version 4, so we're gonna do
Yeah.
all that, and then we're gonna work out whatever buttons for us, respin this thing, because our, Ash Park wants, it's $10 a board, because you're getting, it's pretty decent size, so, but I don't know how to make it smaller, I think I jammed as much in there as I could. So that, I just want to show you that, and then, one of the things that you'll notice